So I decided that I had to take a break. And also because the video got so long, I decided to split up this one incredibly long video into two videos that it's not 1.5 hours long, but maybe, or hopefully, like two videos that are less than an hour. I'll see. I don't know yet how long this video will actually be, but hopefully less than an hour. So where did we leave off last time? So first of all, I showed you guys how you can import the data with the Lab3 functions library function import data. And then we also talked about how to prepare the data, about all those individual steps by using the help or the tutorial from the Scientifically Sound website. And so we did some filtering, we rectified the data. We also, before that, we corrected the mean. So we actually corrected the mean, we filtered the data, we rectified the data. And then in the end, we made an envelope. And then we used the full function on Scientifically Sound that does basically all of those steps. We called it altogether. That basically does all those steps except of the correcting the mean. So what I did here now is to prepare for this lesson today is I just did all those steps for the MVC set, for the weight set, and for the fatigue set. So first of all, I remove the mean for all of those three ones, and then I do the altogether, so meaning the filtering, the rectifying, and the envelope for all three of them. And I do the envelope with a cutoff frequency of 2 here. And yeah, like we said before, we have cutoff frequencies of 20 and 450 for the bandpass filter for when we filter the EMG. So like we don't want to have frequencies that are higher than 450 hertz, and we don't want to have frequencies that are lower than 20 hertz, right? So if I would run this now, this is what we'll get. It's going to be 6 graphs because all of those functions make graphs, right? So this would be the last one. So this is the fatigue altogether function. Then this would be the weights altogether function. This would be the MVC altogether function. And then this is just for the, how did we call it? For the correct mean. Again, the fatigue first, then the weights, and then the filter. Something that we did wrong yesterday, I think here we had, we said we were getting the, can't remember, I think the rectified data, but what we actually want is here, we want the envelope. So, and if you go to Lab3 functions, I think that's what we actually did. Oh, not Lab3 functions, we call it EMG functions. So we made the altogether function here, and then we return the filtered data and we return the envelope, okay? So on this end here, we also need to get the filtered one and the envelope. Okay, so what are our next steps now? So first of all, when we looked at our data, we could see that there's always like a phase of where nothing happens, then there's gonna be some activation, and then there's again some parts where nothing happens, right? So what we wanna do now is we wanna isolate the bursts. So isolating the parts where our muscle is activated, okay? And for this, we also have a function in the Lab3 functions library, which is called get bursts. So I'm gonna show this to you guys now. And it's specifically, again, for this lab. So the function is called get bursts. And it needs, as an input, it needs the filtered data from first the MVC, secondly the weights, and third the fatigue data. And as an output, it will have the starts and the ends of each burst. So let me maybe just start this and then you'll see what I mean with the starts and the ends. So if I run this here, then we'll get a graph like this, okay? And it already explains what you have to do. So we'll have to do what I'll show you guys now 9 times. So first of all, we have to click and then the program starts, right? And then as it explains, we have to click 2 corners to zoom in. And first we wanna isolate the burst of the first, the first burst, which in that case would be from the MVC measurement. So those three are the MVC measurements, right? So I click here once, and then I click here twice, and then it zooms in. And then whenever you think that you have zoomed in enough, you can click enter. So I'm now clicking enter, you can see that, I click enter. And now you want to choose the start and the end of the activity of this burst here. And for this, I don't want you guys to click here. I want to go a little bit inside, that it's definitely somewhere where our muscle was already fully activated. Okay, we want to have the parts that are fully activated. So I will click, let's say here for the start, and then somewhere here for the end. And now we have to do this again. So I click once to start, I click then twice to zoom in, I click enter, and 1 and 2. And then I do this for the third one. Enter, here and here. And afterwards, it will open the same for the weights. So now you just have to remember you already did 3. So now you have to start at the beginning again. It's good that it's the weights in between, because you can see the MVC or all 3 are the same, but here you can see the one is smaller, bigger, and then very big, right? So, and enter, click here and here, and then again, click to start. And I will probably cut the video after this now, and I will do the rest without you guys seeing it because it's ridiculous. Maybe I will also leave it in, who knows? I'll see when I'm editing the video. And that should be the last one. So if I zoom in here, if you make a mistake, you just have to start the function from scratch. That's it, like, and then you just do it again. So if I close this now, if we click on Variable Explorer, we will have some new variables here called MVC start, MVC end, weight start, weights end, fatigue start, fatigue end, okay? So if I go, for example, to MVC start, that is really the data points. So I think, yes, let's do a plot here. If we plot this here now, there we go. So the MVC start, we said, was at of the first burst to start is at 5,291. So if you look here, yeah, that would be somewhere here. That makes sense, right? Then the third burst or the second burst start would be at 18,000 somewhere. That would be somewhere here, and so on, right? And then the same goes for the end. The end is just like the end of the burst. So the first burst ends at 9,579, and so on, and so on. So what we now want to do is we now want to calculate the relative muscle activation of the weights experiment. And the relative muscle activation is always relative to the MVC measurements, right? So our MVC measurements is basically 100%. So that's basically, it's theoretically the hardest that we can activate our muscle, and then everything else should be like, is always lower, right? Obviously, sometimes it can happen that in the MVC experiment, you didn't do 100%, and then all of a sudden in a different experiment, you can get even more. Then you would have 120% or 110% of your MVC. But in the perfect case, everything else would always be under 100% of the maximum voluntary contraction. So to calculate the relative muscle activation, we first need to calculate the mean activation of the bursts of the MVC. So, and this would be how we would do this. So first of all, we need the NumPy module. So let's add this here. Add this here and run it. And then we want to get the mean activation of, let's plot this here again. So we want to get the mean activation of all 3 bursts. So without caring about the stuff here in between, right? So first of all, we need to calculate the mean activation of this part here. And this would be, I would calculate the mean of, and by the way, which I forgot to say now, we're not using the filtered data now. the reason for why we're not using the filtered data, or also here is actually the raw data, or not the raw data, is because if let's plot, for example, the filtered data here, what did we call it? cplt.plot MVC EMG filtered. If you would calculate the mean of the filtered data, it would just be 0 because it's positive and negative, right? So that's why we talked last time about why we rectified, but then we also calculate the envelope. And let's now plot the envelope here. So what we basically need to do is we basically need to calculate the mean of this part here, of this part here, and this part here. So if you look at the code here, what I did is I said that I need to calculate the mean of the MVC EMG envelope between the start of of the first, so that the first MVC start to the first MVC end. So the start is at 5,291 and the end is 9,579. And the 0 is just because in Python, we always start indexing with 0 for the first value, with 1 for the second value, and so on and so on. No idea why this is the case, but this is how coding works. So if we calculate now the mean of this part here, run, then we call it mean MVC1, mean MVC1, then now that's what we get, some 9.9, and I actually think, yes, we can also plot this to visualize it a little bit better. Just for tutorial purposes, we can plot this. There we go. So we basically calculate the mean from here to here, which is the black line is the mean of this. So this is basically our MVC for the first burst of the MVC. I'm not gonna go into detail with this. So what you guys afterwards have to do, you guys have to calculate the mean of the second burst and the mean of the third burst as well. And then you have to take the mean of all 3 of those bursts to have the actual mean of all the MVC experiments, okay? And then the next step is also something that I will not do here. So in the next step, what you basically need to do, you need to calculate, let's plot the plot. So what your next step will be, why it does not. Weights EMG envelope. Oh, okay. So if we run this here now, so now we want to calculate the relative muscle activation, okay? So what you afterwards need to do, you guys need to calculate the mean here, and then calculate the how strong is this relatively to the MVC value. So let's say this one, let's say this is around 1, and our MVC was around 10. So that would then mean that this would be 10% of the maximum voluntary contraction. So you do it for this here, and then you do it for this here. You don't have to take the mean of those two. So you really just take the mean of this and compare it to the MVC. Then you do it for this and you compare it to the MVC. And then you do it for this and then you compare it to the MVC. Then you know what was the relative muscle activation for this part. You know what was the relative muscle activation for this part. And you also know what was the relative muscle activation for this part. So for weight 1, for weight 2, and for weight 3. Okay, and that's how you guys calculate the muscle activation, the relative muscle activation. And now we'll talk about the frequency analysis. Before we can do the frequency analysis, we need to understand what we want to do. The idea for this assignment is that we want to do a frequency analysis for half a second of the beginning of a fatigue experiment, half a second of the middle of a fatigue experiment, and half a second of the end of a fatigue experiment. And the idea is there, if you then compare the frequency analysis of those three windows, that if everything worked out and if you actually got really, really fatigued during those 10 seconds of 100% pulling, then you should see a change of frequencies, a change in the frequency spectrum between the end and the beginning of the experiment. Theoretically, in the end, you would have lower frequencies in the muscle than of the muscle activation than in the beginning. But let's see. So first of all, we need to isolate half a second of the beginning, half a second of the middle, and half a second of the end of the burst, right? Also for this, we will now use our filtered data. So we're not using the rectified and we're not using the envelope because we actually want to see the full frequencies. We're not looking at how much it is activated. We're mainly looking at the frequencies of the muscle. So first, I want to create an array of the isolated fatigue. I think I forgot to mention it before. I mean, I probably mentioned it, but I just wanted to emphasize it again. Now we're not using the MVC data. Now we're also not using the weights data. Now we're actually using the fatigue data, the data where we are supposedly really, 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 really fatigued in the end. So what we want to do is we want to isolate from our fatigue filter data, which looks like this. lt.figure, plot, which looks like, let's see if that'll work. So that's how our fatigue data looks like. And we now want to isolate again, like one of the bursts, right? So since we did that before with the get bursts, we have the start and the end of our three bursts. That is how we can isolate the burst, right? So we say that we want to have from the fatigue EMG filtered data, we want to have the first start to the first end of this data. And if we now say, did I already do that? Let me see. Anyways, doesn't matter. Let's just run this here. Run it. And if I now say plt.figure, then I'll say plot plt.plot array. This is what it's going to look like. It's really just the isolated part here, okay? And what we now want to, we here actually now want to have half a second of the beginning, half a second of the middle, and half a second of the end here. So we need to isolate these parts. So I'm going to show you how we can do that with the beginning. So for the first part, like since we are collecting data with 1,000 Hertz, which means 1,000 data points within 1 second, you can now isolate, or we know that like if you have 500 data points, that will be 500 milliseconds, that will be half a second, right? So I now create, I call it array 05 for half second. You can call it array beginning, array middle, and array end, whatever you prefer. So I'm basically now taking the first 500 data points from the array that I created before. And the first 500 data points will be the first half seconds of this array. So if we actually plot this, let's create a new figure here. If we plot the array and then we plot the array just from 0 to 500, this is what this is going to look like. So we're basically isolating this part here, which is again the first half second of this experiment. And now we want to calculate the frequency spectrum, the power spectrum of this first half second. And for this, I also prepared a function in the lab 3 functions library. I'm gonna show this to you guys here. So what this function basically does, it's called get power. And it takes an array, which should be some EMG data. And it also needs to know with which sampling frequency we're working here, right? So in our case, it is sampling frequency of 1000 Hertz. And we then get the power for the specific frequencies. So if I run this here, oh, it won't work. Run this here. Oh. There we go. So now what we should get is we should get an array called frequencies. Let's see here, frequencies, which has 249 different values. And then let's go in here. So now it basically looked at a frequency of 2 Hertz, of 4 Hertz, 6 Hertz, and so on, up to 500 Hertz, which is half of the frequency that we're collecting with. And then we have the power somewhere, which has exactly the same number, and those values are now the so how strong the frequency is. How strong this specific frequency is. So like for 2 Hertz, we have a value of 90. For 4 Hertz that we had before, we have a value of 92, and so on. And if we plot this now, I actually added the axis here for better understanding. So here we have the frequencies, again, from 0 to 500. Remember Nyquist frequency from the DAQ lecture. And this is how the power is. So in that case, we're somewhere at, I don't know, 30, 40, 50 Hertz where we actually have the highest power. So this is like the most frequencies that happen, or sorry, this frequency is the strongest at the 10 or the 0.5 second data collection. So what we now want to do is we want to filter this data, because obviously it's kind of noisy. So we are filtering this with a low pass filter. Well, let me show that to you guys too. So oopsie, we need the SciPy library. So we add the SciPy library here. Let's run it. So we're creating a Butterworth filter with a critical frequency of 0.08. You'll see afterwards, that's what it kind of like makes it the most realistic and best looking filtered data. And where we want the low pass filter, we want the high frequencies being removed. Then here, yeah, that's the filter itself. And then let's plot it. There we go. So the blue one is our original raw data, and the orange color is now our filtered data, okay? So after we filter it, what we now want to know is let's plot this again. We want to know the median of our frequency spectrum. So the median would be somewhere here. So let's calculate this, and then in the end, and I'll talk about this later, we'll compare the median frequency of the beginning half second, of the middle half second, and of the end half second. So where I got this. So now we want to calculate the median here. There we go. So the median is a function of the NumPy module, and you basically really just calculate the median of the filtered, what I call here power filter, of the filtered power signal. And let's run this. So that should be one value. Power median is one value. So it's actually at 20.9, yeah, so at 21 Hertz. And let's plot this now. there we go. So that's how it would look like. So this is our frequency spectrum, our filter frequency spectrum, and this here would be the median of this specific frequency spectrum. So what I want you guys to do now, and I'm not gonna do this in this tutorial because that would be too much, and it's basically just doing the same again and again. What we want you guys to do is you do the same for like these steps that I did just of all these getting half of a second, doing the frequency and filtering it and taking the median. You'll do this not just with the first half second, but as I've mentioned a few times now, you'll also do it with the middle half second and with the end half second. And then you'll have 3 different median values, and you'll compare those 3 different median values with each other. There's actually, I think, 1 or 2 plots in the lab manual that you can have a look at, and you'll see that in the perfect case, which doesn't always have to be the case, but in the perfect case, it would basically be in the beginning, the median is pretty high. In the middle, it goes a little bit down, and in the end, it actually goes further down. So the median decreases over the 3 over time of one of the fatigue experiments. Might be that it's different for you guys, or because there are a few things which might not go perfectly. Maybe your muscle just didn't fatigue during those 10 seconds, but also maybe it's just a very short experiment, right? So like it can just be that the EMG board just didn't pick up the frequencies or the frequencies perfectly, and it just doesn't work out perfectly, right? So you'll do this for the first burst, and then you'll do all of this again for the second burst and for the third burst. And all of this should be explained in the lab manual. With this, I'm done with the 2 parts of the ECG Python, of the EMG Python analysis tutorials. So again, in the first video, we talked about how we can prepare the data for the further analysis. So how we can filter it and how we get the envelope and so on and so on. And in the second part now, we talked more about how we can do in the end now about doing the frequency analysis to look at the fatigue of the muscle, but also at relative muscle activations. I hope that this video helped you guys. Let me know if you have any questions, let me know too. And I'll see you guys soon. Bye-bye.